In the last video, I left you with one question. How do we implement a queue where you can enqueue and dequeue from both the front and the back? So what if I told you you can do both operations on both ends in O of 1 time? The key to doing this is augmenting your node to include more information than just the value and the next pointer. Let's go back to the problem. Currently, with our implementation, we can dequeue and enqueue at the front in O of 1 time. We can also enqueue at the back in O of 1 time. Dequeuing is simple because you just have to assign the second node as front. Enqueuing is also simple. We can just create a new node and assign it as the new front. And thanks to our new queue implementation with the pointer to the last node, we can also enqueue to the back in O of 1 time. However, if we want to dequeue from the back of the queue, we would have to traverse all the way to the second to last node, and then change the next pointer to point to null so that it will free the last node. We have to start from the front of the list to get to the second to the last node. Because even if you have the last node as your tail pointer, you don't know what the address of the previous node is. You only know what's next, which is null. So what if somehow we can get to the second to last node without traversing the whole linked list? What if every node can access the previous node, just like how every node has access to the next node? So what if with our tail pointer that points to the last node, we can access its previous node and then immediately just detach the last node, hence dequeuing our queue from the back? So the key here is to augment our node, just like how we augmented our queue to have an extra pointer that points to the tail. We can do the same thing on the node structure. Let's add a pointer to the previous node in addition to our pointer to the next node. So now your augmented node looks like this. And the nodes in the linked list look like this. Now you can traverse back and forth all you want. If you decide to traverse your linked list in a normal way, you can do that. But if you decide to go back, you can do that too, without having to start over from the first node. This is actually what we called a doubly linked list because there are two links, one linking to the next node and one linking to the previous node. This idea of modifying the node structure is important because you'll realize that nodes are the basis of many important data structures. You can use nodes to implement a tree or a graph. Here are some examples of how we can augment a node. You can create something called a dictionary node where the node has two attributes. One is the key and one is the value. You can make a priority queue with nodes that contain a priority number. Lastly, you can create a tree node. A node for a tree is very similar to a node for a linked list. However, a tree node can link to more than one node. The example here is a tree node with two children. This is the most classic version of a tree called a binary tree, where bi in binary means two, so two children. Here's what it looks like if you attach many tree nodes together. You can also create a tree that has more than two children. Maybe they don't have a limit on how many children, so we'll use an array of node pointers. Now it can point to as many other nodes as you want. The graph node is actually the same. A tree is actually just a restricted form of a graph where there are no cycles. That means for a tree, you won't have a child pointing back at the parent node or any other grandchildren eventually pointing back at the parent. So a graph without that restriction can look like this with the same node definition. All right, so that was a fun overview of what you can do with a node just by adding more fields to it. Now that we've talked about trees, we'll dive deep into trees in the next lesson.